Okay. So, welcome back, everyone. And if you're new here, welcome. And if you're new here, I just wanted to say that we are a group of physics graduate students at UWM. And once a month during the fall and spring, we do presentations about physics and astronomy here at Anodyne. So today's speakers are me and Shashwat. And if you like those presentations that you were ever in Madison, the UW Madison also has outreach for astronomy. They call Astronomy on Tap. So if you're interested, you can look at them. And today's topic is ancient astronomy. So we are going to talk about how astronomy developed for humans. And before I go to the presentation, I just want to say that if you have any idea for a future coffee shop talk, we can go to your website, and then we have a tab called Contact, then you can write your ideas there. So going back to the ancient astronomy, the first thing I just want to say is that we are going to talk about astronomy, not astrology. So don't ask about the features for us, but if you like astronomy, don't panic, because I am a Capricorn, so you can always say that I am skeptical by nature. So that's the reason why I don't believe it. And the second part of the presentation, we are going to focus more on what did ancient people discover and how they discovered that. But my part, we are going to talk about the history. How did we even get to ancient astronomy at all? And the first thing I want to ask is, did you think humans invented astronomy? And if you think astronomy as a science, yes, science is a very human thing. But if you think astronomy as using the sky to locate ourselves, to track time, so the answer is no, because animals also does that. So as an example, I have here birds. And we know that birds that migrate at night actually uses the stars to know where the direction that they want to travel. So even birds uses the stars to locate themselves. We can pretty well imagine that humans use it even before we can have any record of like human history. So maybe even before we were Homo sapiens, maybe even like before we evolved to be sapiens. So if we didn't invented astronomy, what we can do to track this story is try to find the oldest records we have of astronomy in our humanity. And those are probably what we call the oldest stories. So those oldest stories are so old that we don't even have records of them. We don't have paintings. What we have is the echoes of those stories told generation by generation until today. So one of those stories is the Cosmic Hunt. The Cosmic Hunt is a story that shows up in the constellation of Ursa Major. So Ursa Major is this constellation here. And more specifically in the Big Dipper of Ursa Major, which is a very well-recognizable, easy-to-find constellation in the northern hemisphere. And their story tells that there was this big animal, sometimes a bear, sometimes an elk, depending on the part of the world. And this bear, trying to run away from humans that were hunting it, rises to the sky to hide. And the humans followed it. And then we have the Big Dipper. So here is the animal and the three hunters. But how do we know that this story is so old? Because it shows up in different, of course, with some variations, in the most different cultures around the world. So we have this story in the Americas, in Asia, in Europe. And if we track all the stories and try to understand if they have a common ancestor, what we find is that this story probably originated in Siberia at least 50,000 years ago. And this 50,000 years ago comes because it has to originate before humans come to the Americas. So 50,000 is this lower limit. But some people say that is even older. And actually, the cave paintings we see, some of them are actually depicting the same story of the Cosmic Hunt. And that maybe the story is even close to the oldest cave paintings, so around 50,000 years ago. Another very old story we have is about the Seven Sisters, and probably you know the Greek version of it, which is the Pleiades. Their story tells that there were 7 sisters that were trying to run away from Orion. Orion was chasing them, and so Zeus helped them and put them in the sky so they can be far from Orion. In the end, Orion also goes to the sky, so they are being chased to this day. But this is how the mythology goes. And again, this is a story that repeats throughout several places in the world. So we have this story in Australia, in the Americas, in Asia, in Europe. And because of Australia specifically, if this story also has a common denominator, it has to be at least 50,000 years old, because this was the time where humans migrated to Australia. This story is less studied in terms of how it spread throughout the world, so we don't have like a specific place or time that it developed. But some people say that this could also be an older story. And just as curiosity, the name for the Pleiades in Japan of this myth is Subaru, which is a car manufacturer and also a telescope. So the car manufacturer has this logo because of the story of the Seven Sisters. And I just want to show this video here. Let me see if I can. Sorry for that. So I just wanted to show this video because maybe we are not going to show it. So because we see that they have the Pleiades and Orion, and even to this day, Orion is chasing the Pleiades in the sky. So we told those stories, and they are not just tales. They actually have a practical meaning of existence. And this is because stars are important. And one of the reasons is to track time. So, for example, the Pleiades, they disappear in the sky throughout some months, and then they show up again. For the Greeks, for example, it was the time of sailing. So they knew when the Pleiades show up in the sky again, it was the beginning of the sailing season. And why some stars disappear in the sky, it's easy to see by this GIF. It's not in scale whatsoever. But imagine that it's like we are around this region, and it's night when we look facing that place. We can imagine that even if we have a broad way of viewing the stars that are in the exact opposite, are behind the sun, will not be seen during the night. Only when the Earth moves again and gets closer to them. So some stars disappear in the sky throughout some seasons, and when they reappear again, we can kind of know what time of the year it is. If it's summer, if it's spring, if it's time of harvesting, so we can track time. And another thing that is important with the stars is navigation. So to navigate, we usually use what we call circumpolar stars, so the stars that actually never set in the sky, and this is because they are close to the North Pole. So here, again, to use our stories, we have the Big Dipper. So we see, for example, nowadays, if we use the Big Dipper and move this straight line, we find Polaris, which is the star that we use to know the North Pole. So we can use them to navigate and also track time. So those stories had two reasons of existence. Of course, entertaining people, telling tales, but also because they would make us know where the stars are in the sky, and we could use them for those two reasons. And one thing I want to say is that even though we have those stories that travel throughout all different places, we have some constellations and some stars that are specific of some regions. And some of those stars actually use the darkest constellations. So instead of using the brightest stars, we use the darkest patches in the sky. So one example here we have, for example, the Incas, and also in Australia. And what they see is like those dark patterns that we see in the sky instead of the brightest stars. So we talk about the oldest stories, but we can move forward in time and look about the oldest constructions. So what are the oldest constructions in humanity, and whether or not they have astronomy in them. So even before we have written texts. We have here a timeline. So just so you know, the oldest cave paintings around 45,000 years ago. They are not even fit in this timeline. I would need 3 more timelines, so 4 timelines stacked. And then at the end of the 4th timeline, we would have the cave paintings. So the oldest construction we have is Göbekli Tepe, 11.5 thousand years ago. And it's only here, so we know when the construction started. Some people discuss whether or not it's astronomy related. There's a lot of discussion. It's not widely accepted. So it's not an astronomical site. But we have hundreds of other astronomical sites in archaeology. The oldest one probably is not the Playa in Egypt, almost 10,000 years ago, and it's so old that it's before like the Egyptian kingdom we know. So this is prehistorical Egypt. I'm not going to talk too much about this one. I'm going to focus on those 4 here. And I just want to very quickly show how they are astronomically related. So we have Newgrange in Ireland, and here was a place of worship during winter solstice. So during winter solstice, what happens is that the sun enters throughout this very small door here. So this happens only on winter solstice, and they probably use this place to worship. And Stonehenge has a very similar idea. So we're doing the winter solstice. What happens is that the sun sets in this very special position in the center of the construction. Another interesting one is the Great Pyramids, and what I'm going to focus here is specifically how they align them very precisely with the cardinal directions. So you see here that the north direction is very well aligned with the pyramids. How they did that? And it's not that they align. As we see, we can use the stars to find the directions. It's because the precision is extremely good. We couldn't get them with stars. So one idea is that they use the equinox, and specifically the fall equinox, which is today. So it wasn't on purpose that we choose today for the date of the talk, but it's just a fine coincidence. So what you can do is put like a stick on the ground and trace how the shadow of the stick travel throughout the day. In a normal day, we'll have like this curved shape, but during equinox, we have this straight line here, and this is probably one way that they could get some good precision. And the last construction I want to talk about is in Peru, it's Tranquillo, and this one is a calendar. We're going to talk more about calendars throughout the presentation, but I just want to show up this very nice construction we have in South America. So what happens is that the sun would set in different places of this construction here, depending on the time of the year, so we could know what time it is. So we talk about the oldest constructions, the oldest stories that are so old that we only hear the echoes throughout the stories that were told by generations. Now we can go to the oldest literature. I don't know why literature disappeared here, but we're supposed to be literature in here. So we have our timeline. We're going to update it a little bit. I had to get rid of the construction so we have space. The oldest written records we have are in Mesopotamia, the Kish tables, 5.2 thousand years ago. And very close to it, we have the Nemr palette in Egypt, 5,000 years ago. Those are not astronomical related. And the first part I wanted to talk about literature. So it's not science yet. And for literature, I'm going to focus on the oldest written story we have, the Epic of Gilgamesh. And also in the oldest Greek story, Iliad by Homer. So the Epic of Gilgamesh is 4,000 years ago, so 2000 BCE. And it tells the story of Gilgamesh fighting a lot of monsters. And throughout the story, we have citations of Mercury, Orion, and also an epic battle between Gilgamesh and the Bull of Heaven. And the Bull of Heaven is literally the constellation of Taurus. So the constellation descends to the sky to Earth to fight our hero. And in terms of Iliad, there's a lot of stars being cited in this story. So some of them is Pleiades that we've seen, Orion, the Bear, which is Ursa Major, and also Hyades, which is this cluster here. And one nice thing is that we see that Ursa Major, the Big Dipper, is a circumpolar constellation, so it never sets in the sky. And they have a very poetic way of saying this. So, and she alone is never plunged in the wash of the ocean, so it never really sets. So it's just a very poetic way of saying what we have said with more scientific words. And another thing in the Iliad is that we have this thing about, she gives the name of Orion's dog. Orion's dog is Canis Major, or more specifically, the brightest star of this constellation, the dog star, or how we know it today, Sirius. So Sirius is not a circumpolar star, so it shows up and disappears in the sky, and it shows up again during summer, so the hottest days of the year. And they say here, it's like a little bit of superstition, that those are the times of great fever and sign of evil, so it was during summer. But if you ever heard the expression dog days, the hottest days of the year, it's because those are the days that Sirius rises in the sky again after months being disappeared. So those expressions and those names of those constellations travel throughout millennia to this point. And now we finally get to when astronomy becomes science. So now we're going to talk about the first astronomical texts in Mesopotamia. So again, our timeline, I just added 2 more texts here. So this is where astronomy really began. And it was in Mesopotamia, and more specifically in the city of Babylonia. So Mesopotamia is the whole region. Babylonia is a specific place in this region. So we have Babylonian astronomy. And what they started doing was to do star charts, so tracking when their stars would show up and disappear, and also the planets. The planets has a very different movement. And also eclipses. And during this time, there was no clear separation between what we consider superstition and science. So astronomy and astrology were all together in one. Those texts are not scientific texts, just they are also astrological texts. And there are some things about Babylonian astronomy that actually accompany us since today. And for example, we have the fact that we use 60 seconds in a minute, 60 minutes in an hour, that we call our circle have 306 degrees, and one that is not here, the days of the week being 7. 7, this number, came from the Babylonians. So why 60? And 60 is because it's probably the highest number we can have just counting with two hands. And you can ask how we count to 60 with two hands. So what they did was using the bones instead of the fingers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And to get to 60, we just use the other hand, 12, 24, 36, 48, and then 60. Then we can count 60 with two hands. So it was a good number if you just don't have calculators and you want to do math. So you just use your fingers. And another thing is because 60 is divided by a lot of other numbers. 2, 3, 4, 5, 6. We don't need fractions. It's just another entire number. And 360 is just because it's 60 times 6. So it's, again, a number that has a lot of ways of dividing it. And this is why we have 360 for the circle. So in terms of the zodiac, we know that the zodiac came from them. And the idea in the name zodiac is actually Greek. It's slightly younger. But dividing the sky in 12 parts, and with the 12 constellations we know, is Babylonian. One thing that you may heard of is the presence of this 13th constellation here, the constellation of the snake. And the Babylonians knew about that, and they never really wanted it to be in the zodiac. The zodiac is just a perfect representation of the sky. So we have 360 divided by 12. Each part has 30 degrees. If you divide it by 13, it's 27 point something, and it's like a big rational number. So they didn't want that. So they forgot about the snake constellation on purpose. It was just this perfect way of dividing the sky in 12 equal parts. And again, the constellations doesn't divide the sky in 12 equal parts. So it was never supposed to be perfect. And before I finish my part, I just wanted to talk about historical observations. So until this point, we talk about planets, stars showing up in Babylonian scriptures. But they are things that repeated in cycles. But we also have transient events, like we have comets showing up, we have supernovas. So it's pretty nice that actually we have records of those things in ancient times. So one example is, for example, a supernova that maybe was recorded in India 5,000 years ago. It wasn't in written text, but some people say that this drawing here that we have, one of those things is the moon, and the other one was actually a very bright star that showed up in the sky along with the moon at some point. We cannot ask them if this is true, but there's some people that say that maybe this is a supernova. But what we know is that we have eclipses recorded and also comets. And one thing that is not here written, but I'm going to say, is that actually those things are good to study history. So you may ask how we were so sure that certain events happened that specific year. Because we can compare the astronomical records that are like in history. For example, China saying, we see Halley's Comet someday. And then we know that Halley's Comet show up on Earth around this date. So we know that everything that they wrote around that area is like close to this date here. So it's actually really good to check whether or not we are good on dates in terms of history. And this is my last slide before I move to Shashwat. And I just wanted to show my favorite historical observations, which are supernovas. Funny enough, all of those were observed by Chinese astronomers. And we have this very nice phrase that one of them wrote when they found the supernova in the sky. I humbly observe that a gas star has appeared. So they have records of 6 supernovas, but 3 of them we are not really sure which one it is. So they said we saw a gas star showing up, but we haven't tracked to which supernova remnant those events are. We have like a few candidates, but 3 of them we are exactly sure what was the supernova exploding. So the brightest one is SN1006 that happens in the year 1006. And we have here a modern photo from Chandra, so in X-rays. And it was recorded by several places, so China, Japan, in Europe, in the Arabic world. And actually, it remained visible in the sky for years, and even stayed visible during the day for a few weeks. So this was the brightest supernova ever recorded by human history. And we also have Crab Nebula, which is all of the supernovas here is the most famous. It's a very well-studied object. Nowadays, it's a very interesting object. And it actually exploded in 1054. So again, the Chinese was one of them that observed it, and this phrase specifically is from the supernova. And it stayed visible in the sky for 22 months, so almost 2 years. And another one that we are sure which supernova it is the 1181, so this one, that was observed in China and Japan, and stayed visible in the sky for 6 months. So it's funny that we can actually use those records nowadays to even do current science based on those historical observations. And with that, I'm going to finish my part and pass it to Sasha.
Testing. Okay, cool. Hi everyone. So yeah, Sarah was able to tell us about some of the histories and mythology of astronomy, and I'm here to talk about more of what ancient people learned and the things we've learned since then and some of the things they got wrong. So to start off with, how do we do astronomy when it comes to ground-based stuff? So basically, when you're standing on the ground, everything looks flat, even though it isn't. I can tell you this now. I know it's a contested topic, but so you can see as far as 3 miles in any direction before the Earth's curvature limits you from seeing any further. So when you're standing on the ground, the horizon is as far as you can see. The point right above your head is called the zenith, and you measure things from north, just because it's nice to have a point of reference. So we measure clockwise from north, and that's called our azimuthal angle, and how far something is above the horizon is called its altitude. So this is all really helpful, but it doesn't really matter all that much if you're standing on something that's actually a curved surface. So you need to take into account the fact where you're standing on the Earth, how high or below you are in comparison to the equator. So are you north of the equator or south, and how far east or west you are of something. And our reference point is usually Greenwich. So if you've heard of Greenwich Mean Time, GMT, that's set as 0 degrees on the longitude. So just a fun fact to know. But then again, we're still on the ground, and it doesn't give us the best idea of what astronomy is like. So we need to zoom out a little more when it comes to the planet. So you can think of the sky as just a 2-dimensional projection across the Earth. So we have this thing called the celestial sphere, where we can imagine every star, constellation, and planet appearing. And and the Earth is at the center of it. So you'll notice a few different markings around. So we've got the celestial equator, and that's just aligned with our own equator. And then you've got this thing called the ecliptic. Sarah mentioned this, but what exactly is the ecliptic? The ecliptic is just the path the sun takes across the sky throughout the year. And the reason why it's different is different from the equator is because of the Earth's tilt. So because there's an axial tilt, the point at which the sun travels across the sky is going to look different than just the equator of the Earth. So where these 2 points cross, we get our equinoxes, including today. So today would be the autumnal equinox right there. And then spring, summer, and winter, the solstices would be when it deviates the farthest from the celestial equator. And so we need more points of reference with this bigger sphere to try and understand what we're talking about. So, well, the Earth has the equator, so let's just set the equator as 0 above or below something. And when it comes to left and right, we need another point of reference, and so we use the vernal equinox. So this point right here on spring would be the 0 right ascension, as it's called. And points above the equator are called positive declination, and below is negative declination. So I know that's a lot I've thrown at you, but for an example, as Sarah mentioned, the dog star, when it comes to Sirius, its right ascension is 6 hours, 45 minutes, which means that it's actually facing the summer solstice. So this is 0, 6, 12, 18. And that's how we measure right ascension. And the fact that its declination is negative 16 degrees means it's below the celestial equator. So this is how you measure things when it comes to the celestial sphere and Earth. Okay, so now we know the basics of astronomy and we know how to do it. What do we take as reference points? Well, the sun and the moon are pretty close by, and they're good objects to kind of keep track of how things move across the sky. But the problem is they aren't too constant. So the path the sun takes changes throughout the year. As you can see here, this is what's called a solar graph, and it traces out the path the sun will take across the sky throughout the year. So the points at which the sun is at its highest point would be the summer solstice, if this is a northern hemisphere photo, and the lowest point would be the winter solstice. So the sun isn't exactly a good reference point since it changes throughout the year so much. What about stars? They're a lot farther away, and we can think of them as fixed points in the sky. But the Earth rotates, and as it rotates, the stars move across the sky as well. Except when you come closer to the poles, because it's where the Earth's axis is, those stars will not trace out the same large distances across the sky, and so they're what we call circumpolar stars, like Polaris, the North Star. Because it's so close to the Earth's axial tilt, it doesn't move that much as the Earth spins. And Chinese astronomers figured this out in the 3rd millennium BCE, and they began to use them as well. So just a nice picture of what the northern and southern hemisphere look like in the sky. So here you can see this is the northern hemisphere, and that's where Polaris is. So that's our northern star situated nicely in the middle. And then we've got the southern hemisphere with the Southern Cross and other such constellations. So what did ancient people do with all of this knowledge? Quite a bit, actually. They were able to figure out quite a few things. Specifically, this one man named Eratosthenes was a Greek smart guy who was able to figure out the radius of the Earth. And he did this by having shadows at 2 points a very large distance apart. And by measuring the angle produced by the shadow, he was able to tell what the circumference of the planet is. And if you have a circumference of a circle, just divide by 2 pi and you get the radius. And he was able to get it within very, very close accuracy of what we know it is today. And this was done way back in like 2,000 years ago. So this is very impressive stuff. Indian astronomers by the 3rd millennium BCE, so 5,000 years ago, knew about the 5 planets other than our own, as well as the sun and the moon. And one famous Indian astronomer, Brahmagupta, who is mostly credited as inventing the number 0, also came up with the concept that maybe bodies of masses attract each other, so gravity basically, and also came up with equations of parallax. So what is parallax? Parallax is just how something changes when you change your point of view. So the audience kind of looks like it's sitting this way, but if I move my point of reference, the audience has shifted. And by telling how much of a shift it is, you can see how far something away is. And this is how scientists still measure the distance of some stars to this day. So the Greeks were also able to predict solar eclipses, and they thought that maybe the moon isn't giving off its own light, but is reflecting the sun's light. So they're making some progress here across the years. As Sarah mentioned, astronomy is extremely useful, especially when it comes to navigating the sea, especially for Polynesians and the ancestors of Pacific Islanders who would set sail into the ocean without knowing where they were going to end up. It was extremely important to know what the night sky looked like so you could track your position through it. So this is an example of a Polynesian star compass, which would help them navigate the oceans. And another great example is this guy named Pytheas. Pytheas was another Greek smart person who traveled up north to around England, was able to calculate the latitudes of where he was, as well as the position of the Arctic Circle to within 1 degree of what we know it is today. So he's a pretty contested issue, and none of his own work survives, but we have indirect references from other people who have done stuff with his work since then. So, and also he has one of the first accounts of tides ever written down, about tides in England and how they shifted and flowed. So, yeah. Now, moving on to timekeeping stuff, So Sarah's mentioned it's obvious people were able to keep track of days, months, and years, but when you wanted smaller counts of time, you need something that like a clock. Well, before the clock was ever invented. So one of the oldest things people think of is a sundial, and one of the oldest existing ones was from Egypt in 1500 BCE, so 3,500 years before today. But one of the most valuable timekeeping devices was actually a water clock. So this works on the principle that water flowing out of somewhere at a constant rate would give you an idea of how much time it takes to drain one container, fill the other container, and these were used all over the place. So they were used in Egypt slightly after the sundial. They were used in the Indus Valley civilization, as well as by the Babylonians around the same time, 4,000 years ago. So it's extremely valuable, and the Chinese have been using them for over 2,000 years as well. And since then, they've made improvements to their clocks. They even managed to upgrade one of their water clocks into a mercury-based clock 1,000 years ago. So, pretty crazy stuff. As Sarah said, the Babylonians are responsible for the 7-day week, so you should thank them while you get a 2-day weekend. And that was in 2300 BCE, so extremely long ago. And something that really surprised me was when it comes to timekeeping devices, you'd expect that the hourglass would not be far behind all of these other great inventions, but the hourglass was invented very, very recently, only about 600 years ago, so something pretty interesting to think about. And now, talking about calendars, we've talked about smaller units of timekeeping. Now for the longer stuff. Sarah kind of touched on this with the pyramids and other such locations that constructed these things, but one of the other oldest calendars is Warren Field in Scotland, and this was constructed 10,000 years ago. In 8000 BCE, 5,000 years before the first Mesopotamian calendars would be around. They would take into account the phases of the moon as well as the winter solstice, something similar to Stonehenge, as Sarah mentioned, but way, way before. So this is incredible work done by ancient people. So moving on, more calendars, some of the more recent stuff we found out. So Indian astronomers were able to split up the day into a year into 360 days, and then some little more. And as Sarah mentioned, it was a big deal to split the year into 360 days. We'll see that coming up further. Callippus was a Greek astronomer who actually tried to keep track of both the lunar and solar cycles to match them up. And he's the reason why we know a year is approximately 365.25 days, because he used such long count calendars and then divided by that. And we can also thank Julius Caesar and this guy, Augustus or Gaius Octavius, for our naming convention of the current calendar we use. So these were not the original names of the months. July and August were named much later, and the original Roman calendar only had 10 months. And you can actually see a consequence of this because of the last 3 months they originally had. October referencing 8, November referencing 9, December, Deca referencing 10. So they originally only had 10, and January and February were added in much later. So let's talk about Mayan calendars. I know everyone's kind of freaking out right now. So about 9 years ago, something happened and people were really scared. So let's talk about it. Mayan calendars are really interesting because they use a bunch of different base units to construct their calendars. So like the Babylonians use 60, the Mayans would use base 20 and then switch it up with base 18 and all kinds of crazy things. So they actually had an 18-month calendar with 20 days each, and 5 nameless days, which were thought to be very ominous, and spirits would walk the earth during those times. So they had that as a calendar count called the Hab. Then they had longer calendar counts that would consist of more years, such as 52 years. They had some cycles going up to 63 million years worth of counts. So they had a bunch of different base units. talking about December 21st, 2012. Why was everyone so freaked out about that? Well, the reason was because it was the end of one of these cycles, a 394-year cycle. So you can see today's date is actually 13.0.10.168.8. So on December 21st, 2012, this date was 13.0.0.0.0.0. So that's when the calendar reset. And the next time this happens will be in March 26th, 2407. So you can expect some doomsday stuff to come around by then too. Uh, yeah, so now moving on to one of the coolest sections, in my opinion, is just the tools that were available to the ancient people and how they used them. So some of the oldest and most interesting devices are the Antikythera mechanism. And this was discovered in a Roman shipwreck off the coast of Antikythera, Greece. This is an analog computer built by people nearly 2,000 years ago. And so it consists of these 37 bronze gears. This is all that's left after being underwater for so long, but it consists of 37 bronze gears that would each model a planetary body throughout the solar system. So this is an analog computer, and it's crazy because it could predict solar eclipses as well. And something even older than that is the Nebra sky disk, which was found in Germany, and it's one of the first depictions of astronomical phenomenon on this brass plate. You can see it's aligned with the summer and winter solstice. You've got sunrise and sunset, and you've also got what might be a reference to the Pleiades up here with this cluster of 6 stars. So another reference to one of the oldest stories as Sarah was talking about. Moving on to some other astronomical tools, which such as astrolabes. So astrolabe is this device right here. Of course, this is a much more modern version of an astrolabe, but you can use them to track star positions. And they were invented in Greece nearly 2,000 years ago as well. Then you've got armillary spheres, which were invented in China. So these are these sets of concentric rings that kind of spin and move, describing motions of planets. And they managed to get them water powered over time. So it's really interesting stuff, creating a computer basically. And the first compasses were also built in China using lodestone. So here you see a magnetic spoon right here. So this is one of the first compasses ever built. And here's just a picture that's pretty interesting. The flag of Portugal also has an armillary sphere built into it. So moving on to somewhat more of the future, about 1,000 years ago. So as we mentioned, the Chinese used a lot of water clocks, and they managed to get them clock towers water powered, such as this 11th century one, which is extremely big. And this is around the time that you can also see the Islamic world having its influence in astronomy, math, and geometry. So here we have a celestial globe from the Islamic era, as well as an astrolabe from around that era. So we kind of lied about the sky being the same all the time. The sky's changed quite a bit since ancient people first looked up at it. And how exactly, you might ask, has the sky changed? Well, we don't look at the same pole star ancient people saw. So because the Earth's axis isn't completely fixed, it wobbles, it precesses, it completes a circle every 25,960 years. So within that time period, you kind of reset the Earth's axis back to where it originally was. So 5,000 years ago, when the pyramids were being built, they were not looking at Polaris at all. They were looking at this star called Thuban, and we are looking at Polaris. And in the next 2,000 years, our descendants will no longer be looking at Polaris either. They'll be looking at Gamma Cephei. So the pole star is going to be changing throughout the next tens of thousands of years. And because the Earth's axis tilts, the tilt of the Earth's axis changes, our equinoxes will also change. Our seasons will kind of shift positions. So another reason why you shouldn't trust your star chart is every 71 years it's going to be about a day off. So they're only good for around a lifetime. Um, so yeah, this is an example. You can see present day we've got spring, winter, fall, summer, and within 10,000 years, all of them are going to swap places. Now you'll have fall where spring once was, you'll have summer where winter once was, and this will keep happening over a course of 26,000 years. Every 26,000 years, our seasons will swap and then come back to where they started. So this means that constellations have changed also. Constellations aren't nice two-dimensional diagrams that we imagine them to be. Here you can see what the Big Dipper looks like if you change your perspective on where you stand. So it's a bunch of three-dimensional stars arranged together, which means that some of the stars closer to us will change faster than the stars farther away from us. Here's a representation of what the Big Dipper and Orion will look like 100,000 years from now. So they'll look a little more wonky, and we'll probably have to come up with new stories to describe what they are. So clearly, ancient people thought of great things and they used their intuition really well. But they haven't gotten everything right exactly. So let's discuss some of the stuff they weren't quite able to nail. So the Greeks about 2,500 years ago thought that the the sky consisted of these tubes or rings of fire, and these rings would have little holes through which light would pour in, and those were the stars, sun, and the moon. So obviously it's not the best idea, but then they shifted up to spheres, which is a little better. And along with that, a lot of cultures, along with the Chinese 1,000 years ago, believed in the concept of a celestial lid, something like a dome that would cover up the sky. A lot of cultures believed this. And one of the most prevalent things was geocentrism, so the Earth being at the center of the universe, which isn't exactly a terrible idea because it's the only reference point you've ever had, so it makes sense to think that you are at the center. But because you believe you're at the center, the planets around you don't follow neat cycles you'd expect them to, and so you need to keep making your model more complicated. You need to add in epicycles and more epicycles to kind of account for retrograde motion, so on and so forth. And here's an example of why that doesn't really work. Yeah. So here we've got a nice geocentric image, the sun at the center, the earth moving around. Here is what happens when we place the earth at the center. It's kind of weird. Things are doing weird things. They're not following nice orbits, and it's hard to explain. You could come up with a model for this, but it would be extremely, extremely complicated, and there's a simpler explanation at the end of the day. We're not at the center. And so, yeah, so now moving on to the future, the medieval era, is when we get the Islamic Golden Age. So what began with translating other people's work turned into developing their own methods and coming up with their own theories, and even doubting the Ptolemaic model, the geocentric model. So Islamic astronomers had begun to doubt if this was the correct way to describe the solar system. And they also began to correct the axial precession that was thought to have been there earlier, as well as wrote extremely influential works which would go on to change the course of European as well as Asian astronomy. And eventually they would lay the groundwork down in optics for the building of the first telescope, which would change everything. So now towards the end, we just like to focus on the future. Since this is mostly about ancient astronomy, we're just going to run over these guys because you've probably heard about them. So we start with Nicholas Copernicus, who came up with the Copernican revolution, or the model of heliocentrism. So he was one of the first people to solidify the fact that the Earth was not the center of the universe. And he was thanked for this by being burnt at the stake. So it didn't go very well for him. Then comes this man named Tycho Brahe, who's a very interesting fellow who had a brass nose because his own got sliced off. Look him up. He's a pretty interesting figure. But he was one of the first people to observe and coin the term new star or stellar nova, which would go on to become supernova. And he took tireless, really detailed observations of planets and bodies in the sky, and his work would go on to lay down the foundation for this man right here, Johannes Kepler, who gave us the equations of orbits and how planets actually move in the sky. So his work led to his work, and at the same time, two spectacle makers would end up independently creating the first telescope in the Netherlands, but it wasn't used for astronomical purposes at first until this man, Galileo Galilei, invented his own version of the telescope and pointed it at the sky. And this is where everything changed. And Galileo is extremely famous for this. So we've gone over ancient astronomy and how far we've come, as well as just a recap of the stuff that happened in the middle of those two events. So some of you might say, well, astronomy is done. We've figured out everything there is. That's not true. There's still thousands of years more to go ahead and discover. It was only around 100 years ago that people first looked up and realized we are in our own galaxy and there are other galaxies out there. So it wasn't very long ago that astronomy started to really be looked at in a different manner. And now we're using technology that'll look even further back in time. So who knows where this timeline will go. And yeah, so this is the last slide. So yeah, thank you so much. Questions at all? So yeah, it's I think if for the right ascension, that's a naming convention that's stuck where you stick with the hours, but you can easily convert into degrees just by saying, well, there's 24 hours is 360 degrees. So yeah, it's just a convention that kind of stuck along.
Ways of measuring angle in astronomy, and we use both. We still use radar centers and declination, but we also have a galactic way of measuring angles that are with the 360 degrees we imagine. But if you look at articles nowadays, both of them show up.
Yeah. So those are used for Earth-based measurement. Yeah, and those are usually in degrees. Oh, sorry. That's a good question. I don't think I don't know the answer to
Maybe
that one.
because England was important.
Hmm. Yeah. Yeah. Thanks. I didn't know that. Um, Yeah.
Haven't seen it, so I'll try. I'll try next time. I'll go to Brazil. So we have, and thank you for the stories. They were
Yeah.
really interesting. But we see how astronomy actually influence our lives, and we don't even know, like clocks being clockwise because of sundials. There's any other questions that anyone may have?
Oh, uh, going once. Oh, okay. All right. Well, thank you
Thank
everyone
you.
so much for joining us.